for attending this. I just want to say that my goal here is really just to learn from all of you. I have my own project that I'll talk about, but I don't feel like I have some definitive answer to just go with here. So I'm really excited for this. I hope we can do this almost more like a lightning talk format, except in a BOF, because I don't have any better ideas for how we can learn from each other in this crowd class platform. I'd like to remind you, there's a 15-second delay between the experience of the people on video and the chat. So just be aware of that time shift, especially as you come in. You're going to be shifted in that way. And I guess we're going to go through, hopefully most of the people that put their name in the Google document are around. And initially, I hope we can just spend about 5 minutes just talking about what we do with hardware and what packages we use, what we're thinking about. And then maybe we have some time at the end to just chat broadly as a community as what seems to pop out for us. So I work for the University of Wisconsin in Madison. I work for the chemistry department, and I'm in research support. So my job is enabling custom instrumentation for the chemists in our department. We have like 40 faculty or whatever. And my passion is removing the barrier that software development often represents to combining the hardware that people have in interesting ways, or driving a set of hardware in a way that hasn't been done before. It's really frustrating to me because I work a lot with making custom hardware, and then it's even more frustrating when you can't even do the thing with the custom hardware that you made because the software's in the way. So that's kind of my big picture thing. I work with Kyle Sunden, who also is from my university, on a project called Yak, which is a kind of a framework where each individual hardware interface runs in a daemon. So it's a separate little Python application running in the background, and clients make RPC calls over TCP to those daemons. And the reason that's so great and I'm excited about it is because these individual daemons as separable applications are portable and very transferable. So there's a lot less duplication of effort when I can create a Yak daemon for a certain class of hardware. I know that I can reliably drive that hardware on any machine. And then for front ends, I tend to use PySide2, Qt, PyQt graph. That's kind of my stack, I guess, for creating a graphical user interface. So, that is me. And I'd like to hand it over to Kyle, if that's okay.
Hi, so I'm Kyle. Like Blaise said,
Kyle is frozen for me. Are you there, Kyle?
I am. I can hear you.
Okay. Why don't you go, Mike? You're moving for me.
Sure. Kyle's working for me, so.
Oh, really? Okay.
Yeah.
So.
Sorry. Let me reload.
I will just start talking. So like Blaise said, I work with him. I work in a laser spectroscopy lab doing multidimensional frequency domain laser spectroscopy. So we have a lot of different light sources, tunable lasers, and we have different delays and mirrors that we have to move in order to get lasers overlap different laser beams in the same pulsed laser beams in the same point in space and time. So this is a configuration problem, and we built Yak with this in mind. So Yak, and there's a poster on Yak if you are so interested. So Yak uses traits, which are collections of methods and configuration of information in order to enforce that similar types of hardware work and display their functions in the same manner to a client program. It's a multi-client interface, so you can have multiple connections to the same underlying hardware daemon, and it can work on remote machines as well. So, yeah, that is my story in this realm. I'm going to let Mike take over from here.
Sure. My name is Mike. I work at Nthought. Some of you may have heard of Nthought. We've been interested in the intersection of software and hardware, theory and experiment for doing material science. And we've been working in, generally we help industry research clients utilize these kind of digital tools, utilize the scientific Python software stack. That's where we started out a lot of our work, building custom solutions to do all sorts of things. But recently we started getting interested in hardware, like this Birds of a Feather is discussing now. And how do we merge these worlds of software and hardware? We have some tools similarly, internal tools similar to what we just heard about with Yak for doing instrument control. It's not super well developed yet. It's all kind of a new area for us, but we're kind of working in this realm where how do we marry these two components? And so to help build a community around this, we recently started this initiative called the 1000X Lab, which I'm going to paste the link in the chat. It's got some information about an event we held, but the idea is to try to build better automation tools, lower cost, that have the right kind of interfaces and APIs for working with Python tools and software tools that you guys are probably all familiar with. I have a video about this event on Friday's, agenda for the material science track. We have a 25-minute video where I'm discuss sort of our efforts on this event. I encourage you, if you're interested in this, contact me either by email, LinkedIn, through the 1000X Lab website. We're definitely interested in building a community around low cost, more open lab automation hardware for doing research. So we're looking forward to your guys' input on.
So can I ask, Mike?
Sure.
How does the Python angle get into the hardware? Is Nthought actually developing physical instruments? Is that what you're talking about?
We've done some. Primarily, we were doing things that's like makerspace kind of hacker hardware. So we do a lot of 3D printing for like custom optical microscopy and things like that. There's tons of other projects out there already, especially with Raspberry Pis and the Raspberry Pi camera. It's a very cheap entry point into imaging. And so you can build all sorts of custom tooling around that. We've also gotten into some other projects outside of microscopy, into some more advanced things around printing and things. But it's kind of early in our work in hardware, but there's definitely an opportunity in this space for building kind of tailored or custom hardware tooling like you do, but for sort of industry researchers to do things a little bit differently. And this is also beneficial for academics. There's academic groups out there doing very similar activities. We're definitely not the first or only people working in this space.
That's going to be a theme, is everyone has a pet, but people aren't talking to each other. At least I don't see, no one's talking to me. I guess that's all I could really say.
Yeah, no, for sure. There needs to be more community and like a go-to place where everybody knows, oh yeah, you can go here to find like-minded people. So yeah, we're trying to start building that community. Obviously, SciPy is a great place to do it as well.
Great.
But yeah, that's my pitch for come watch the talk on Friday and come talk with questions at the Q&A. All right, who's next?
Yeah, thank you, Mike. I guess Dan.
Hi, can you hear me?
I can hear you.
Great, that's probably good enough. Great, so I'm Dan Allen. I work closely with Tom Caswell, who's next in the Google Doc, but has thrown me under the bus to speak for the team here. We work at a U.S. Department of Energy user facility, which means we have some scientists on staff, but we primarily service users who show up for a week with a box of samples and take their data and go home. So you should imagine roughly 30 semi-autonomous research groups, like academic research groups, each with their own instruments, wildly different data rates, techniques ranging from microscopy to tomography to scatter. And what they share is they're all using X-ray radiation to perform their experiments. So there's a shared X-ray source with lots of different science happening. Tom and I both happen to come from the more small-scale lab bench optical microscopy world, and we're really enthusiastic about SciPy and open source. And so we've worked on this project that we call Blue Sky. I'll put a link in the chat, whose purpose is to get the data from the instruments all the way to a NumPy array with all the context that you would need to use all the tools that we love in SciPy to analyze that data. So capturing the metadata and the context. And we've tried to do this in such a way that you can grab the pieces that are useful to you and just use those. So there have been some smaller academic groups that have just picked this up. Apparently a telescope in Australia, an X-ray beam in Korea, a couple other US labs have started using the pieces that are useful to them and giving back. So there's a little bit of a community there. We'd love to make some new friends here. I think SciPy feels like sort of the home of this project to us. And I'll leave you to poke around at the link, I guess, to learn more about it.
Yeah, Blue Sky and OFID, and I think it's Trunk. I haven't got a chance to try them, but personally, I've kind of decided the next time I build a new instrument or reactor, I want to build it with Yak for the low level, which is what I'm kind of already, that's where my personal momentum is. But then I want to try Blue Sky for all of the business logic and data recording. And I really appreciate that that's possible. That's how you've made things modular. And bridges, Thomas Caswell says, yeah, there's a nascent bridge between Yak and OFID, which is Blue Sky's like generic hardware interface.
Yeah.
Anyway, I'm a total Blue Sky fanboy, even though I haven't actually used it yet.
That'd be fun. Well, it'd be nice to keep pushing on those bridges when we all get a chance to do it. I think in reality, a lot of us need to push on the things where our focus are, but at least we can steal ideas and reuse pieces as much as possible, right?
Okay.
All right.
Thank you so much.
I'll sign
Dan.
off then. Yep.
Calvin.
All right, can you hear me?
I can hear you.
Excellent. Okay, there's not much of a delay between speakers, I feel like, but between the chat and the speakers, there is a bit of.
It's a yeah.
So my name is Kelvin. I'm a postdoctoral researcher at the Center for Astrophysics at Harvard and Smithsonian. I primarily deal with kind of saddling between a couple of different, what's the word, like disciplines, I guess. So I sit between chemistry, astronomy, and more recently more into the machine learning kind of side of things. And so from an experimental, I'm a trained experimentalist. And so what I'm interested in is gas phase spectroscopy of very transient and very unstable molecules, which are of interest in space. And so the experiments that we do kind of utilize high-speed oscilloscopes and high-speed arbitrary waveform generators. So the same kind of stuff that you would use for radar jamming. And the kind of stuff that we're interested in is typically kind of frustratingly gated behind either very expensive hardware as well as very expensive software that kind of locks you out of certain functionality as well. And so what I'm interested in, unfortunately, I don't have so much to bring to the table right now, but I would be like interested in hearing, how people are interfacing instrumentation, as well as I think people have already touched on this GUIs, which I guess is something that has a million different ways of solving in Python. And so personally speaking, I think I would like to start investigating more into controlling experiments in a browser. So whether or not, Dash or kind of dashboard like control interfaces would be feasible for these to automate experiments.
My one reaction I have is, applause. I think the future, or one future that I'd be really excited about, is one where we have persistent programs that are doing low-level hardware I/O, and then we have the multiple transient, lightweight, maybe browser-based clients that you can just log into your instrument like you could any other web app and do something and then walk away.
Right now we're doing control through like VNC, but we can actually still run an experiment remotely. But as you say, imagine like a Jupyter Hub like system where you just run daemons all the way down and a bunch of microservices serving your instrumentation. But thanks for having me on. I'll sign off.
Thank you, Calvin. Thanks. Eric.
Hey there.
You're up.
So welcome to my basement. I guess I'm coming from a little bit of a different approach than most everybody else who's spoken already. So we're not using Python to directly control low-level aspects of hardware. It's kind of higher up in the software stack. And so I was really interested in I looked at the blue sky, the kind of like the stack diagram that was in there. And so we have our own I'm sorry, a little bit of background. I'm the project manager for the wavefront control or the wavefront correction system on the Daniel K. Inouye Solar Telescope. So my background is electrical engineering, and I've worked in a field called adaptive optics for like the last 20 years. And what we end up using Python for, number one, analysis all over the place, but that's not involved in running our system. Where we've ended up using Python was a way to write calibration scripts for our system so that we can automatically control the devices. We have 26 motors in our system, and we only move those really during calibration, and that's all done via Python. And this was it was a hard road to get here, but it was really worth it. So our main control system is in Java, and Java sits on top of, or it uses something called 0C ICE, which is the message. It's basically a message passing system that lets you create this distributed control system. So we built a control system on top of that using Java, and we call it our Common Services Framework. And then within that, we have something that we call a calibration sequencer. And basically what it does is spin up a Python interpreter. Well, how do you do that when you're running in a JVM? And it turns out we use something called JEP. It's Java Embedded Python, and I'll put a link up as soon as I'm done for that. But that's really cool because it allows you to run a real Python interpreter through JNI, and you have full access to the SciPy stack. So we had access to NumPy because a lot of the things we do in adaptive optics, they're image based, and we need to do during calibration. We need to do real time image processing, not in a high rep rate sense, but we want to grab an image and process it. And what we originally had done was we were using what the heck is it called? Jython, because we couldn't use Python. We were using Jython to run in a JVM, but you can't run NumPy inside of Jython. So then we started using OpenCV because you could get to OpenCV from Jython. But that wasn't with OpenCV. It's got advantages, but it was like programming in a straitjacket, at least for us. And so we gave that up. And with this JEP, we were able to use Python. And so we have a whole set of calibration routines, and they're actually activated from our Java control system. So a user sits down at the user interface and clicks a button to run a particular calibration, and it pulls the script out of our script store, which is a database, and then fires up the interpreter and runs it. And from that, and we actually have access to Java, so we can directly interface with the control system and execute commands to move the motors. And like we can control, for example, we have something up in the top end of the telescope that has sources, light sources and targets and things like that. And we can control that so that we can calibrate our system. And it's all been working really, really well. So anyway, that's where it comes from. And then I use Python for all our GUIs, and this is totally outside of the control system. And I ended up using a combination. I use Qt, PyQt5, and then a mishmash of PyQt and Matplotlib. And I was able to do real-time image acquisition and display like 2K by 2K images that come off of one of our cameras, and I can display that at 10 hertz in PyQt but you can't do that in Matplotlib.
PyQt is awesome.
Yeah, and so then, but some things look much, much nicer in Matplotlib, so I used that I could generate some really nice like strip charts and bar charts and certain things. So anyway, that's where I'm at and what we're doing.
I feel like one thing I noticed is that it seems like institutions like yours, Eric, where you have huge, complicated networked instruments that you are working on over generations almost, those kinds of instruments have been more successful doing Python. I'm here on the many small experiments thing, and it's all LabVIEW all the way down,
So we don't have LabVIEW, but I think we're in the middle of this transition where many people use MATLAB or IDL.
Yeah.
And we're slowly getting away from both of those, one from a cost point. Yeah. There are people that have used IDL inside control systems. So
yeah. Well, thank you, Eric.
All right. Thanks, everyone.
Appreciate you sharing with us.
All right.
Well, who's next, though, actually? Do we have someone else next? Oh, yeah, here's Adam. Oh, bye, Eric. I think you're muted, Adam. If you hover over your face, they should have some opportunity to change that. skip you. Matthias, is there? Oh, here's Zachary Buchanan.
Yeah, hi.
Hello.
Not much to say. I'm a spectroscopist in the University of California, Davis. Most of what I do is like the physical building of instruments, and then we have like my boss has written a lot of the software that we use for controlling our instrument, but he did it using Qt Creator with C++.
Mm-hmm.
I like Python better. He doesn't, but so I've done a little bit of that, and I've done, like you were just saying, LabVIEW. I've used that in other labs I worked in, and I kind of hate LabVIEW. So anyway, so mostly I'm here because I am interested in using Python to control the instruments and learning what other people are doing and learning about different opportunities for that. So I don't have a lot of experience with, I've used Python for data analysis, but not in terms of instrument control. So I'm just here to learn. Hopefully.
I think, as Eric pointed out, a lot of the reason so many of us want Python to be in the instrument loop is because the SciPy ecosystem has so much power for online data analysis that you could start to do much more complex and sophisticated control loops and active process stuff. So yeah, welcome, I guess.
Thanks.
Nice to have another spectroscopist. I'm curious, so the actual interfacing, whether it's like commands over serial or driver calls with the hardware, is that built into the C++ in your boss's?
So his software it's called Blackchirp. I think he's got it on GitHub, but it's built into that, and he's got all of these classes and packages so that you can easily add in a new piece of hardware into your system and the GUI that's all kind of packaged together. So you do have to, I think you have to go through and specify what the different ports and commands are in the serial commands, but once you do that, it's pretty easy to implement it into the actual GUI for controlling the instrument.
Sounds very familiar. Do we have James? Hello, James.
Hello there. How you doing?
Pretty good. Happy Tuesday.
Yeah, I thought I'd give some from the UK. You might be able to tell from the accent. So, I work for the British Antarctic Survey. So we actually use Python in quite a lot of different contexts. So we've got an AI lab who obviously use the scientific Python stack a lot more than I do.
Okay.
But I'm quite interested in machine learning and all of this. But more interestingly for this talk, I suppose, is that we have a lot of experimentation, obviously, down in the Antarctic. So more and more, I've been trying to implement small microcomputers with Python stacks on them. And I think that's quite an interesting line of research because these low power devices can obviously sit out with a load of batteries and solar power and do some pretty interesting stuff. Especially in remote locations where we don't actually have bases or people on the ground. So I think there's it's really worth investing in a standardization of the platforms we put down there.
Are you talking about like full fat Python on like a Raspberry Pi, or are you talking about MicroPython?
No, full fat Python. So we actually use something called, or one of the experiments I've been involved with was with using Technologic TS7400s. So they're little ARM-based microcomputers, but they run a very old version of Debian, but it's enough to, sort of interact with a satellite communications modem and sort of fling some data back, because obviously you've got no internet, so... but I think there's a lot of scope, especially with ever increasing power on small devices like that. we build them using Ansible. So, we're using DevOps technology to build standardized experimentation, stick a Python platform on it. And we have NumPy on there. So, we do a bit of number crunching, get the data.
That's awesome.
Yeah, and then fling it back. But I think one of the big problems we have one of the big problems there is going forward is that a lot of academic projects will sort of redevelop that wheel over and over and over again. And it's massively frustrating. So,
yes.
This is why I did the build with Ansible. It was like, well, we might as well build 10 of them and then fling them at the engineers and the scientists and see what they can put on. There's quite an appetite for it in the UK. So hopefully we can keep that appetite growing.
Okay. Do you have a link for us, or is there anything public about your project?
There is not. You can go to the BAS website, actually. If you go to the BAS website and have a little look at, currently we relay GPS data back from the Halley research station. So if you have a little dig under there, there's a project called Lifetime of Halley. I'll dig out the link and stick it in the chat in a minute.
If you could.
That will sort of give you some public information about how we're using devices, and there's a whole realm of other projects related to that, because currently Halley is an unmanned base, so we actually have a microturbine generating power and powering our VSAT down there. So there is Python all over that. So we use it for control systems, we use it for data analytics on the power systems.
Wow.
You can do an awful lot with Python, so that's why we love it, right?
Of course.
Yeah, I'll stick a couple of links in once I'm off the video.
Thank you, James.
Thank you.
Great contribution. Cam.
How's it going? I'm Cam Gerlach. I'd be very interested also to see those links because we're actually doing something not nearly as cool, but sort of similar. So I'm as you know, I'm a PhD master's student here at UAH in Rock City, Huntsville, Alabama. Also a NASA-funded researcher working on several products. One in machine. The two main ones. One is in deep learning, and one is in building an IoT sensor network. So I built something called. What we had to do, it all started with this array of lighting sensors, and we wanted to send back real time telemetry and data from the power system, because it was all solar powered, data from the actual sensor, health and status data, and information, and actually be able to control the sensors remotely. So I started out building this kind of bespoke client, as one often does for that particular application, and writing, starting with some scripts and actually building it into an actual Python package, making it deployable, but very bespoke to this application. But then I met several other researchers from our university who are building other sensor networks. In fact, one of them is called eMesh, and actually it's going to be potentially up to around on the order of 1,000 sensors all across the state that several agencies are funding. And that actually will be used in real time. So we actually found with several other groups as well, we found a lot of common ground. As you all have recognized, there's a lot of core needs and core infrastructure when it comes to especially low cost, high density scientific sensor networks that, especially with scientists who don't have a strong programming background, it's a lot to rewrite that over and over and over for every application. So what if we had a framework that would allow you to have a core API a simple API that allowed you to say, okay, here's an input, here's an output, how to actually get data from the sensors to the cloud or to your server or to your computer. And we're basically building something like that called Product Milner. We actually have a presentation on the Earth Science block that goes up Wednesday night, and we'll take questions there. But yeah, really this whole work was motivated by some common challenges, and that a lot of you guys have faced. And what you guys have built here, like with the whole stacks often focus a little more on kind of heavy duty, high end instrumentation versus IoT sensors, but
yes,
we're trying to bring a common framework like that to IoT, scientific IoT. And really what I really hope to see with Mueller going forward is not just have it be just one CAM's project, if you excuse the pun, but which is, I mean, it's really a number of teams are going to be involved here. But what we really want to see is a whole ecosystem developing of presets and plugins that allows us to essentially encode our knowledge about all these all these small, low-cost, low-power sensors that you can get from companies like Adafruit and SparkFun. You can attach to, say, a Raspberry Pi, essentially encode not only the protocols for accessing like I2C or SPI, but all the core data about the sensors. We support metadata like the tolerances and the units, and which can process with a product like Pint, and essentially building that into a declarative preset file for each sensor that allows you to basically plug and play. You just say, hey, use this preset. It'll load it'll actually install the right dependencies. It'll load the class, and it'll log the data and record it into a standardized class that you can take in your pipeline, which we've also built this whole pipeline architecture that you can then run at extra processing steps, and you can easily create plugins either with Python packages or just with a simple Python. It allows you to insert your own steps into the data processing pipeline and write your own input steps, write your own output steps. So you can take this, and just by plugging in the hardware and adding a few lines to a config file, you can get your own IoT scientific sensor network all set up and recording data, and you can start analyzing this. So that's the whole dream, and hopefully we can get the community involved building presets, building plugins, contributing, and creating something really cool.
Yeah, I'm impressed at how many of us have come to this idea of plugins and what you call presets. Hardware is harder in that it's just ever more idiosyncratic, right? And even if we come up 5 years from now, we're in some brave new future where we have some one true package that covers 90% of hardware, there's still going to always be unique or even custom hardware. And that extensibility is so important. I really like the idea of extensibility on like a communication protocol level, and actually having different hardware interfaces running as different processes on a machine, because that goes beyond even it can be multilingual even, but yeah, that's awesome. And IoT sensor networks are more and more relevant, so I think what you've created is awesome.
Well, thank you. Well, you guys are even more awesome. So
well, awesome all around. Are there other people who wanted to chat or talk at all?
Not that I can tell.
Let's see. Best we can hope for is common interfaces, as Epix and NumPy have done before us. Yes, I agree. I really like Yak's traits system that, basically in Yak, everything is a procedure, right? So you have a protocol, you have basically these functions, these methods you can call, and the traits enforce consistency between those methods. Epix is very powerful, but I did not feel capable of implementing it for the instruments that I was working with. Matthew, what's up? Would you like to share some?
Yeah, so I work on a cosmic microwave background telescope it's located in Chile at a remote observing site. So the actual detector readout, the high data rate stuff's all written in C. but the glue code that controls everything and the readout for all like the housekeeping system for like cryogenic thermometry, read the generator status, stuff like that is all written in Python. And one of the things we have is a Django based web interface that schedules all the observations and controls it, and it makes a huge difference. I don't know how we'd run this thing thousands of miles away without a web interface.
Is there anything you could share from that stack? Or is it really custom?
It's really custom. I mean, the actual hardware is, a lot of it's like bespoke electronics. So there are some commercial, we've got some stuff like SRS and stuff, but the main thing we use to control everything runs a system D services, and then we use the Pyro 4 Python remote objects library to essentially expose Python commands over the network, and that's how we control things. And then all the data ends up getting written either locally to disk or over NFS to log to the central server.
So you use Pyro between devices. Wow. Oh, wow. Do you guys hear that?
We use it between services on the same device, and also between different servers.
I see.
A lot of the hardware can be controlled over the network, though. So essentially the central server just runs the services for each of the pieces of hardware that can be controlled over the network and controls it that way. But we do have some stuff on separate machines, and we use the same interface for locally versus over the network. Of course, we have some hardware too that, like the cryostat itself, is controlled by a LabVIEW program that we only have the Windows binary for.
Yeah.
So we have to run a Windows virtual machine just to run
that's
the
so
binary
relatable.
and connect over RDP to actually control this thing.
Yeah, that was one of the things in Yak that we wanted, was an interface that was not specific to Python, just in case there were those pieces of hardware that you can't interface with any other technology.
Right, so we have some other stuff like that, but essentially you just use a Python shim layer that just controls it and exposes it and makes life easy.
Yeah. So what ideas do people have for how we can turn, I don't know, seems like maybe 10 to 20 people here that are interested in this kind of thing into an actual community with momentum? So that's a real question.
So there is a group on GitHub, and I'm pulling up the link.
Sorry.
It's you can talk while I'm doing this.
I just wanted to say thank you, Matthew. And Matthew, it seems like your team has converged on the same pattern that many of us are kind of dreaming of or building towards in various stages of that building of, a web client and then microservices running Python for actual hardware I/O. So something to point out.
The link that I posted was it's a GitHub group that grew out of mostly microscopists that have started to gather together to discuss some of the problems in this field, and also just collect lists of projects that exist.
I don't think anyone ever put anything. Oh, someone put projects I mentioned. I had a cool project section at the end of the Google Doc, but that seems to have been a failure. Will this be record? Can I watch this back later?
I believe we can. Yes.
I think that's true.
So,
I'm not sure the chat will be recorded. So if there is anything in the chat you want to keep. you may want to save that somewhere.
Yeah.
So we have the Google Doc, but yes, I mean, as long as Chromecast, you can come back to Chromecast and you can replay, and the chat replays at the same time. You can even click on the message on the chat and it will jump to the right place in the video. But that's as long as it's on Chromecast. And I don't know how long it will stay there.
So if anybody has questions that they want to ask the group of people who's gathered here, please feel free to ask a question on Crowdcast, and we can have.
It seems to me, and please correct me, chat, there's like 3 big projects that are trying to be a thing. There's Blue Sky, there's Yak, and there's Molineer, which I can't say. Is there one that I'm missing? It's a big one, or one that's trying to like solve the problem generally, or Mole. Do you know how to say that, Kyle?
I can never pronounce it correctly.
Hammer, but unfortunately, that doesn't help me say it. Yeah, awesome naming convention, Cam. I wish I had a cool naming convention. What is the history of Blue Sky's name? Does anyone know that? Oh,
well, does Dan or Tom?
Thomas, Dan must know that.
Okay, we get coming back to try to pronounce it.
Okay. Oh,
it's Project Mjolnir. It's like Thor's hammer. And in fact,
Mjolnir.
The client is called Brocker. And the client's called Brocker, and the server's called Sunji, which are the 2 dwarves that originally crafted the hammer. There's a bunch of other stuff that has names related to that.
Oh, that's so cool. Say it once
the
more.
original Mjolnir. I think I'm not an expert. And the other thing is our lightning network is actually called Hamma. So of course, Mjolnir is the lightning producing, at least in the Marvel comics, a hammer of Thor. And of course, it's our lightning sensor network. And he can summon it from any distance just by holding out his hand. So it's kind of a blend of different syncretic traditions there from between comics and like Norse mythology. So you can summon the data from Mjolnir from your sensor all the way from around the world as we have them deployed. So, and I would not say we're a big project either. We're a pretty small project, but not you're
looking at 90% of the contributions to Yak on screen right now. So,
well, it sounds so much.
I feel like Blue Sky is the only thing we have that's actually what I would call mature.
It's also one of the only ones that's more full stack, because Yak is handling, Yak and Mjolnir are handling hardware communication and that layer of it.
So can I invite a Blue Sky dev to come and directly tell this community what to do? Because I think they're going to be better at it. I'd also like to put on the table that I would be open to sprint on this broad topic if there's something useful to be done this weekend.
Obviously, Tom, you're going to be busy on the actual sprints days, probably.
Probably. Can you hear me?
Yes.
Yes.
Okay. It's always amazing when audio on Linux works.
It's getting better.
Right. So now that I've been through the time warp.
Okay. The question was, what can we do? What is your perspective? What would you recommend new people or people with baby projects do to try and build towards something sane and scalable, and hopefully something that, at least to some extent, capitalizes on Blue Sky?
So I think that when we look at the space, there's at least 3 or 4 problems that need to be solved simultaneously. Right at the bottom, I've got special Snowflake hardware that needs some very particular bit protocol to communicate with.
Yes.
And then you've got like some middle layer where you really want to run orchestration across a bunch of motors and a bunch of detectors. And you'll be able to talk to all of your motors the same way, independent of how you actually talk to them on the wire. You then want to run kind of hardware agnostic scientific plans, right? If I say I want to run a spectroscopy scan and I want to move my illumination from this wavelength to that wavelength, you should be able to switch which laser you're using or what exact piece of hardware you're using for that. And the science logic shouldn't even know the details of those between them. And then you have a data management layer on top of that where you've taken all this data. And when you start thinking about the downstream analysis problem, there's so much metadata that you have to collect at collection time, because that's the only time you know it correctly. That if you lose, if you lose what the exposure time was, good luck calibrating your images. And so at collection time, you need to make sure that the system refuses to take data without taking all of that important metadata down somehow. And then the next layer up is getting that back out and start having tools that's aware of all this stuff and can exploit all that metadata to do better science. And